Right, hello. So this week's video is on the subject of L and R values. So if you know what L and R values are, this video is probably not for you. If you've not come across a term, it may well be useful, and if you've worked in C++, there is a decent chance you've come across the term in an error message at some point. Now I will say that almost all languages, whether compiled or interpreted, have some sort of concept of something a bit like an L value and an R value. But we are going to be talking here in terms of C++. We're going to be using C++ terminology. And I'll try and explain the concepts in a way that applies to other languages, but that's not something that can be made completely generic. So, as I say, there's a decent chance that if you've come across the terms but don't actually know what they mean, you've come across the terms in the context of C++ error messages. So let's first of all create a program that generates one of those error messages, or perhaps better put, let's first of all write a program that works and then modify it in a way that produces an error message, but it might not be immediately clear why it causes the error message. So, very simple program. Just something to let me print, and then I'm going to create a very simple function I'm going to call demo that takes a reference to an integer. Okay, and then it's going to increment that integer. So bear in mind, in C++, if you pass a reference to a variable to a function, then inside that function you can modify the value of the variable, and that value change propagates back out to the variable you called the function with. Now, some programmers say that's a bad idea, but people do it, and here it demonstrates a point quite nicely. Okay, so I'm now going to create my main program, and I'm going to create an integer variable called I with a value 0. I'm going to call my demo function with I, and then I'm just going to print it. Okay, very simple program. Compiles first time. Run it, and I get 1. 0 plus 1 is 1. That's what I expect. So that's a program that works. Now, what happens if I switch this I for a 1? And the answer is it refuses to compile. With an error message, it talks about the L values and R values. And it says, rather unhelpfully, cannot bind non-const L value reference of type int ampersand to an R value of type int. So we'll just go through that bit by bit. So cannot bind, that's just it saying this function expects one of these, you've provided me with one of these, I can't make that binding work. I cannot call this function with this parameter. Okay, so non-const L value reference. So non-const, you may well have come across const in C++. Const is basically a guarantee that something isn't going to change, isn't going to be modified. And here it's so non-const reference of type int ampersand. So what that is saying, the function expects to be called with a reference that can be modified, and in fact I am modifying it, of type, of a reference to an integer. And that's just telling me what I already knew, but it's telling me it expects an L value reference. And what I provided it with is an R value of type int. And that's sort of the idea. If you go back in history to a language even before the creation of the C programming language, the terms L value and R value originally show up, and it is in terms of things that are evaluated in left-hand mode or right-hand mode. So in left-hand mode, you're talking about things on the left-hand side of an equals sign. Equals here being assignment, not testing for equality. So things on the left-hand side of an equals are things that have to be able to store data in them. There has to be some part of the computer's memory that refers to the place, that is the place where that value is stored, so it can be modified. And on the other hand, you had things on the right-hand side, which are evaluated in right-hand side mode and were R values, which were things that didn't have to have a particular storage place in memory. They could be things like 1, 2, 3, just constant numbers. And over time, as languages have changed, those terms have modified slightly, and so now you have the term L value, which means a value that has a storage location. And in fact, nowadays, L doesn't mean left-hand, it means a location value. That's a terminology usually used. And over time, the value for the things that aren't L values have changed. For a while, C in particular just called them non-L values. But we're going to use the C++ terminology, and I'm in fact going to be fairly precise. I'm going to call these things PR values, which is a value that does not have a storage location. So the P means pure. It is a pure R value. It is a value that never has a place in memory that it is stored in. You cannot meaningfully talk about an address in the computer's memory that stores that value. And now you can sort of see why this isn't working. So the idea is the function expects to be effectively handed a place in the computer's memory. That's what a reference is. And I'm instead handing it just one, a number. And that is one of these R values or PR values. It does not have a location in memory. So that's what that error message means, and that sort of describes the problem. If I want to pass a pointer or a reference to something, then that has to be something that has a memory location that I can get a pointer or a reference to. And the compiler will complain if it can't get one. At this point, I will actually just take a brief diversion from C to Fortran and show that Fortran has the same problem but doesn't detect it anywhere near as elegantly. Okay. So what I have here is I have a subroutine which I'm going to call demo again, and it's going to take I, which is an integer, and I'm going to do I equals I plus 1. And then I'm going to create my program. Change some names to make these things work. And I'm now going to call demo with the literal. And I can compile that. And it compiles, but it crashes when it runs. Because the same thing has happened. Fortran is an intrinsically pass-by value language. So again, here, this I refers to a particular place in memory. But because I've passed it a literal, a 1, it's a place in memory. It's not a real place in memory because it is an R value, a PR value. C++ detected it a lot better. It is worth pointing out that Fortran is not intrinsically unable to detect these. If I put an intent statement on my Fortran, it will also refuse to compile with a rather more helpful error message of non-variable expression in variable definition context. So this is not an intrinsic weakness of Fortran, it's an intrinsic weakness of very old-fashioned Fortran, which is what I wrote initially. But we're mostly talking in C++ today. So I've been very definite to talk about L values and R values, and I've now introduced this new term of a PR value, a pure R value, a thing that never has storage in memory. So why do I need to make this separation between a PR value and an R value? And the answer is because there's another type of thing. So I'm going to copy my test program, and I'm going to make some changes. So first of all, that non-const thing, as I say, if I put const in here, I promise that I am not going to modify I. At which point, even though talking about taking the, the address to getting, passing a reference to 1 is meaningless, the compiler can work that out. It can make it work. However, I can't now just increment I because I promised here with this const that I'm not changing it. So I will instead return Okay, return I plus 1. And I now instead do here, like that, and that will work fine. And I now get 2 because I pass in 1, it adds 1 to it, returns it, and I print the result of that, 2. Now, imagine that what I want to do instead is not store the value I want to have a pointer to I. Pretty mad for an integer, might not be completely mad for larger objects where you don't want to actually copy them. I will say normally, well, I'll explain that actually a bit later when it makes a bit more sense. So I've told it that I is a pointer to an integer, and I've said I should be the get a pointer to the return from the function demo, and I'm then going to print the dereferenced pointer here. And it's complaining again, and it's saying L value required as unary ampersand operator. And that again makes some measure of sense. You are saying that you can only take the address with the ampersand operator of something that is an L value. It has a storage location. So that's fine, except that feels very peculiar. Because inside this function, I definitely am calculating variables. You expect them to be put somewhere when they return. And they are. In order, there has to be a place in memory set aside for the result of this function. But the way functions return, we've mentioned in previous videos that functions work by creating stack frames, and part of the stack frame is the return value from the function. So when the function is finished, the stack frame goes away and that variable disappears. And this introduces the reason that I've been talking about PR values in C++ rather than R values, because there are also these things called X values. And an X value is a value that is going to go away. The X comes from expire. It is a value that is going to expire on its own. It's going to go away once that function has, in this case, once that function has finished evaluating. There are other forms of X value, other ways of creating them, but a return value from a function is a good example. And so in C++, an R value is either a PR value, i.e. a value that never has a memory location associated with, or an X value where the location is going to go away immediately after this thing has finished evaluating what it's doing. And neither of those can usefully have pointers taken to them. And there's a lot of subtlety built on top of this, and it is worth noting that there are an awful lot of things that this doesn't cover. So this is all talking about the properties of proper variables being used properly. If you try doing invalid things like returning a pointer from inside a function to a variable that's only defined in that function, then that return is not an X value, it's not an R value, it's not an L value, it's just invalid. You've done something wrong. But this does explain certain things in the way C++ does things. So you might, for example, have come across the idea of using the function standard move, and you use that to flag whatever I put inside standard move shouldn't be copied into a variable. So I'll just put in an example of doing it. None of these make a lot of sense, but if I make I here an integer again, that compiles and runs. And the idea of this standard move is I'm saying whatever I have inside this function, don't copy it into I, move its content into I. Now, for something like an integer, moving and copying are basically identical. But if you have a complex class that has its own internal storage, moving would just take the data that's inside the second class and move it, the right-hand side here, and move it to be owned by the left-hand side. And as a general rule, this is something that C++ will always do if it knows that this assignment is an X value on the right and an L value on the left. It has to be an L value on the left, otherwise you can't meaningfully assign to it. And that's what standard move does. It converts an L value. So if this thing here on the right was actually a valid storage location, so, if I, for example, here create I2, I'll do I2 is 14, and I get rid of this demo 1, that works. And it has moved the value from I2 to I. And it does that by moving I2, which is initially an L value, it has a perfectly valid storage location, and making it an X value. It is about to expire, and hence all of its internals can be optimized. You can optimize moving it into I in a way that normally you'd only be able to do with something that you already know is going to go away, like the return from a function. So this is related to things like return value optimization and various other ways in which the compiler can optimize things. And so that's a very quick run through L values and R values, particularly how they apply to C++, with a brief diversion into Fortran. And that's the important thing to remember. If you come across an error message that mentions about L values and R values, try and read it in those terms. Are you at some point trying to use a variable that is either temporary, it's an X value, or somehow is not something that's going to be stored somewhere in memory? It's a literal value, something like that. And are you trying to then use that in a way that only makes sense if you're talking about something that has a true storage location, i.e. get a reference to it, get a pointer to it, or, quite a few things. There's quite a few elements that are only possible for L values. And that's basically it. So hopefully those error messages are less mysterious than they were before, and we will be back next week.